Hi, welcome to our presentation. The aim of our presentation was to be able to implement a keyboard and a VGA display in order to change the colors of a screen depending on the keyboard input. And it uses sequential logic because there's memory associated with each key, and it remembers the colors that you put before and the present color. So one of the modules that I worked on was the top module, and this module sort of takes the inputs from Yihe's keyboard, which takes like an 11-bit number that represents each key on the keyboard, and then we narrow it down and it outputs sort of a 3-bit number that represents one of 8 colors, which is black, white, red, green, blue, and then combinations of those red, greens, and blues. This also implements an HV sync that I made a module for, which basically sort of changes each of the pixels on the VGA display individually, and it uses the clock to do so. So it goes across a certain amount of pixels horizontally until it reaches the end. It knows it's the end because there's an input for the amount of pixels. And then there's a little bit of a gap area so that once you go over to the next horizontal, there's enough time to do so. And then it keeps repeating that horizontal movement until it reaches the end of the vertical. And there's also gap time for that so that it can come back up to the top of the screen. And then within that, we can define a display area, and the counters do so and keep track of sort of the coordinates of that. And we implement that back in the top module. And depending, again, on these keyboard inputs, we're going to have a color displayed.
I'll introduce the keyboard module. So it's basically takes in data from the PS2 port and 3-bit output to represent 8 colors. So the PS2 ports have only 2 input wire, one is clock and one is data. So when each key pressed, the PS2 data port will actually take in 11 bits and use 8 of them as data, and that's what they have for the R, G, B, and Y. So that's only 4 keys that we're using. So what's good about this code is that it can represent the combined colors. So here, there are some registers representing whether if red is on or green is on or blue is on. So if red is pressed and not green, not blue, it will just be the color red. And if red is pressed and green is on, then it will be red plus green, which will be yellow. And those colors will be like combined to get a new color. And that's how the keyboard module works.
So it connects to a keyboard and VGA display through the ports on the board. And on the keyboard, we are using W, R, G, and B. R represents red, G is green, and B is blue. White is for reset. It will start with a black screen, which represents no color. And we'll press red, it will become red. And we'll press green, it will add the green color to the red, so it will be yellow. And also if you add blue to the 2 color, then it will be 3 color combined, which is white. And you can reset and do, for example, blue plus red is purple, and green plus blue. So you can do any combination of those 3 colors. And that's basically how it works.
Our code works like, say, state machine, because it remembers the states of like red, green, and blue. But when we're actually implementing it, it's not like structured as a like proper state machine. So maybe there should be 8 states like representing 8 colors, and
Basically, that will be a Moore machine.
And that makes the code looks better.
One of the things that we realized quickly that we needed to improve on, and the reason why the top module didn't originally work, was because this if statement wasn't there, and it was defining whether it was in the display area or not. And if it was outside that display area, because there's time allotted within the counter that's not within this display, or not within the counter, but within our pixel allocation that's not within the display area, then it wouldn't display the proper colors, because that's the amount of time to shift over. So by adding this piece of code, we were able to get it to work.